Hi, so in this video we're talking about linear independence and when to identify when a bunch of vectors is linearly independent. So, to recall what it means to be linearly independent or dependent is vectors are linearly independent if you take a collection of them and there's no way you can make one of them by combining the other two, right? If I take all the ways I can move up and down or left and right here, there's no way that I can put those together to get an outward movement like this. So this set of vectors is linearly independent. On the other hand, linear dependence means that I could combine two of the vectors in such a way so I go across and then up to get or two or more of the vectors to get one of the other vectors. So that's linear dependence. So in the context of this problem here, these vectors are linearly independent if there's no way I could take like these four and get this fifth one, right? That would mean linear independence. Linear dependence would mean that I could take these four and somehow put them together to get this one. So, with that in mind, let's go ahead and address the question. We want to take the statement, the original statement, rephrase it in terms of a vector equation, and then ask ourselves, is it true? So, based on what we just said, linear independence would mean the vector equation and now we have to kind of go here, and so we have 5 of these vectors, minus 5, minus 4, 0, 3, minus 2, minus 4, minus 4, minus 2, minus 1, minus 3. Five, 0, 1, minus 6, 2. And then fourth, the claim now is that there's no way I could combine these 4 vectors here, right, which were these first 4 vectors here, to be equal to this last vector here. And so our claim is that this equation has no solutions. That's what it would mean if these vectors were linearly independent. And so now that we've rephrased this in terms of this vector equations, we're right back to our earlier problems of solving systems of equations or vector equations. And so what we want to do is break out our trusty augmented matrix and see whether or not this vector equation in fact has a solution. So let's go ahead and write out what our augmented matrix would look like. Blah, blah, blah. Minus 4, minus 4, 4, minus 2, minus 1, 3. 5, 0, 1, minus 6, 2. Minus 6, minus 2, minus 4, minus 6, minus 3, augment, minus 5, 2, 4, 4, 4. Alright, so far so good. So since we have all of that, let's go ahead and break out one of our technological tools. As before, right? Minus 5, 4, minus 2, minus 1, 3, 5, 0, 1, minus 6, 2, minus 6, minus 2, minus 4, minus 6, minus 3, and that's our 4 vectors on our left hand side, and then our final vector on the right hand side of our vector equation, minus 5, 2, 4, 4, 4. And what we have then as the reduced row echelon form matrix is just ones across the diagonal and 0 elsewhere. So what we get is that the reduced row echelon form of our augmented matrix is of this form. And as we've noted before, the key thing to observe is that this bottom line here implies that in order for this to have a solution, 0 would have to be equal to 1. And as we recall, that's not true ever, right? And so since the above vector equation has no solutions, these vectors are linearly independent. All right. Thank you very much. See you in the next video.